Electron configurations are a way to try to describe where the electrons around an atom are located. So it's something that everybody who takes chemistry is familiar with and has seen, and probably nobody truly understands. Quantum mechanics is very complicated, and it's a complicated math that is used to calculate these clouds of probability that tell where you're likely to find an electron. It's not like an orbit of Mars around the sun where there's this pathway to follow and we can predict exactly where Mars is going to be at any point in time. It's not like that. We can't predict where the electron is going and which direction it's heading. We just have a cloud of probability. But we name these clouds according to the principal shell, which is a number, 1, 2, 3, 4, etc. So it goes from 1 on. And then also a sublevel or a subshell. And that is denoted by a letter. S, then P, and then D, and then F. And then if we needed them, we could go down the alphabet a little bit more, G, H. But we don't ever need that many. I was taught with the mnemonic, slow people don't finish geometry homework, so then after F would come G and H, but S, P, D, F for slow people don't finish. So the first sublevel S has one orbital, and each orbital can fit 2 electrons. So each box fits 2 electrons. So each of these boxes that I'm drawing here can fit 2 electrons with opposite spin. So the electrons are usually shown as an arrow, one pointing up and one pointing down. So in 101, we go a little bit more into these quantum numbers. The number for the principal shell, the sublevel, there's another number for each of these boxes, and then the spin is a 4th number. And there is a Pauli exclusion principle that no electron can have the exact matching 4 numbers as any other electron in the element. So in order to get 2 electrons into the same box, they have to have a spin number that is opposite so that the numbers don't all match. But the important thing for us to remember is that each box can fit 2 electrons. Anything that's an S only has one of these boxes. So the 1s orbital, the 2s orbital, the 3s orbital, any one of these s orbitals, the 1, 2, and 3 being the main level. So the main level 1 has an s orbital, the main level 2 has an s orbital, and so on. And each of these s orbitals has one box and can fit 2 electrons. So we'll just put that s orbitals can fit 2 electrons. Then p sublevels have 3 boxes, so they can fit 6 electrons. So sometimes I give the comparison of filling up boxes of seats in a theater. So if people are walking into the theater, if there's somebody sitting here, you might leave a little space, and then the next person to come leaves a little space. But then as the theater gets more and more crowded, then people start doubling up and filling up the empty seats that had been left by the first batch of people. So altogether, the P can fit 6. In a similar way, as you fill up the D, it can fit 10 electrons. And then the F with 7 boxes can fit 14 electrons. Not every main level has all the different sublevels. So as the main number increases, these shells are getting further from the nucleus of the atom, and they're getting larger and larger. And so they can fit more sublevels as you go along. So level 1 can only fit an S sublevel. It cannot fit a P sublevel. Level 2 can fit an S and a P. Level 3 can fit an S, a P, and a D. Level 4 can fit S, P, D, and F. So level 5 can fit S, P, D, and F. And then if we had enough electrons, maybe even G, we don't have any elements that go out this far, so I'm putting this part in parentheses. 6 can have S, P, D, and F. And then I just started drawing the 7 just so that I can show you the answer to question 4 Chem142 Lec4.5.1. So these orbitals fill up in order of increasing energy. Again, it's like buying tickets to a play. If you had a theater with different seating sections and you started selling tickets to those seats and all the tickets are the same price, then the first people to buy tickets are going to buy the best seats in the house. And then the next people to buy tickets will buy the next best seats, and so on and so on. There's no reason why someone would walk up to the window and take bad seats when better seats are available. So that's what electrons do also. They fill up in order of increasing energy. And I've drawn this as a triangle as a little helpful diagram to remind us what is the order of increasing energy. So if you want to just memorize this, you can, but this is a rain on the roof method of remembering what the order of increasing energy is. So we're pretending we have kind of this triangle roof, and then we're going to have some rain falling on this side of the roof. And the rain is going to fall diagonally. It's like a storm. It's being blown against the roof diagonally. Okay. I already used blue, so for the rain I'm going to use purple. We'll have some purple rain over here. So the first rain that falls hits the 1s orbital. And then the next one falls and hits the 2s orbital. And then the 2p, and then the 3s, and then the 3p. And at this point, you're kind of in the same order as if you just read them off a normal way from left to right. You don't really need the diagonal rain. But at this point, instead of 3d coming next, if you were just reading this as a list, after 3p, the 4s is actually lower in energy than the 3d. So the 4s orbital will fill up before the 3d. And this could happen in a theater as well. Maybe the center seats in the fourth row are better than the edge seats in the third row. That can happen. So the 4s orbital is actually better than the 3d. So after 3p comes 4s, and then comes the 3d, and then we're back to 4p, and then 5s, and then comes 4d, and then 5p, and then 6s. So now this gets a little bit difficult to remember if you were just reading them this way. You need the diagonal lines. Or another way to remember this is with the periodic table. I can show you that next. So after the 6s comes the 4f, and then the 5d, and then the 6p. So this is the order of the orbitals, the order in which it fills up, because this is the order of increasing energy. If you want to think, these are the best seats in the house, then the next best, and next best. So this is the order in which the tickets are going to sell out. Your online textbook, LibreText, in section 4.5 actually has a pretty good illustration of how to use the periodic table to remember the order of orbitals in electron configurations. So the first orbital to fill is the 1s, that's the lowest energy, as we mentioned. That the first 2 electrons go in there, so hydrogen with 1 electron and helium with 2 electrons are putting their electrons into the 1s orbital. Once you get to lithium, there are 3 electrons, and so we need to start the next orbital. They don't all fit in the 1s orbital because s orbitals can only fit 2. So 2 electrons fit into s orbitals, and you'll notice that this part of the periodic table, this wall of the castle, is 2 blocks thick. That's because these elements are filling up the s orbital. So here we have lithium and beryllium filling up the 2s orbital. And then we jump to boron over here. This thicker wall of the castle has 6 columns, and 6 is the number of electrons that fit into p orbitals. That's because these elements are filling up their p orbitals. So these next elements are putting their electrons into the 2p orbital. And then again, we have the thinner side of the castle filling S and the thicker side of the castle filling P. Then we go back to filling S. This sunken moat area of the castle is where we're filling the d orbital. There are 10 columns here, and there are 10 electrons that fit in the d orbital. The only thing is that after the 4s, we don't fill 4d, we fill 3d. We're going one level behind to fill the d orbitals. And then we go back to level 4 and start filling the 4p. So we have 2 columns for s orbitals. They fit 2 electrons. 6 columns in this area because these are filling the p orbitals. 10 columns in this area because these transition elements are filling the d orbitals. And then down here, the lanthanides and actinides are actually filling the f orbitals. That's why there's 14 columns here. So just remember, I'll make a note on here. Remember that this d block is one level behind. So this is the 4s because this is period 4. So the s area and the p area match the period. We have 3s, 3p in period 3. We have 4s, 4p in period 4. But in period 4, we're not filling the 4d, we're filling the 3d. So the d is one level behind what the s and the p are in that period. So 6s, this is where the lanthanides are inserted. After 6s, we are filling 4f. So the f block is actually 2 levels behind. So in period 6 is where we're filling the 4f. In period 7 is where we're filling the 5f orbitals. So the f block is 2 levels behind, the d block is 1 level behind. But once you remember that, you can actually use the periodic table to write these in order. 1s, here we have 1s being filled, and then 2s, and then 2p, and then 3s, and then 3p, and then 4s, and then 3d, and then 4p, and then 5s, I didn't write that, there we go. And then we are one level behind 4d, and then 5p, then 6s, then 4f, 5d, and then 6p. So this is how far we have to go, remembering the order of the orbitals. And so you can use that rain on the roof method that I showed you, or you can use the periodic table itself to try to remember what order these go in. Let's take a look at problem 4.5.2 and draw some electron configurations. So for some of the simpler ones, I'm going to go ahead and draw orbital diagrams. Orbital diagrams are when you actually draw the orbitals as boxes. Here we have the order of the orbitals. First comes the 1s, then 2s, then 2p, and so on. And here is an orbital diagram showing the 1s orbital for helium. And for neon, we'll do this as well. And neon will need the 1s, the 2s, and the 2p. That is because helium has 2 electrons. If you look on the periodic table, you can find that. And neon has 10 electrons. So 2 electrons, if there's 2 people buying tickets for the show, they are going to buy the best tickets. The 1s orbital is the first one to fill up. And it can fit both of those people. So here's helium. And the 2 electrons of helium are both located in the 1s orbital. For neon, there are 10 people, or 10 electrons, 10 people buying tickets to the show. So the first 2 people buy the 1s tickets, the next 2 people buy the 2s tickets, and the next 6 people buy the 2p tickets. And that gives you 10. 2, 4, 6, 8, 10. So all of the electrons of neon can fit in the 1s, 2s, and 2p orbitals. So again, that's an orbital diagram. the electron configuration would just be the name of the orbital, the 1s orbital for helium, and then a superscript to show how many electrons are in there. Helium is the 1s orbital with 2 electrons in it. Neon has the 1s orbital with 2 electrons in it, the 2s orbital with 2 electrons in it, and then the 2p orbital with 6 electrons in it. So this time we'll just do electron configurations for the other ones because there's a lot of electrons. This would be a lot of boxes and arrows. This is how many electrons these elements have. So the first ones to fill up are the same order as this 4.5.1. So they all fill up in the same order. The thing is that there are more than 10 electrons, so we just need to go further. So 3s with 2 electrons brings us up to 12. 3p with 6 electrons brings us up to 18. So we're filling these orbitals up in order. Remember that the s can only go up to 2. Once you are more than 2, you have to go to the next one. The p can only go up to 6. D's can go up to 10 because there's 5 boxes for a d orbital, if you remember the previous page, so it can fit up to 10 electrons. And then F can fit up to 14. So up to. This can be less than or equal to 14. So these D can have fewer than 10 electrons, it just can't have more. So these can all be less than or equal to these numbers. The superscripts have to add up to the total number of electrons. So for argon, these superscripts have to add up to 18 because argon has 18 electrons, and we're showing where all 18 of them are. 2, 4, plus 6 is 10, plus 2 is 12, plus 6 is 18. So all 18 of argon's electrons are accounted for in this electron configuration. So for krypton, we are starting the same way. We're filling these orbitals up in the same order. We're just going further. So after the 3p comes the 4s. 2 more can fit in there, bringing us up to 20. Then the 3d comes and we can fit 10 in there. That brings us up to 30. But then we still need more, so we can do the 4p. 6 more brings us up to 36. And then for xenon, we have to go even further than that. So we have 2, 4, 6, plus 6 makes 10, plus 2 makes 12, plus 6 makes 18. Here we're up to 20. Now we're up to 30, 36, 38, 48, plus 6 makes 54. So we have enough to take care of xenon here. So now we're going to answer one last question on the number of valence electrons these elements have. So the valence electrons are the electrons in the outermost shell of an element. The reason why we're paying so much attention to the electrons of an element is because the electrons are located on the outside of an atom. So when atoms come together, when they start to react together, bond together, things like that, then that is the electrons that are doing all of that, because that's the outer shell. The outer coating of an atom is the electrons, and that's what they use to deal with other atoms and other elements. And of that shell, the outermost shell is the most important. So these valence electrons are doing the most chemistry, and it's important to know how many valence electrons each element has. So for helium, the outermost shell is 1. It doesn't have any 2s electrons, so it's the outermost shell is this level 1, and there are 2 electrons in level 1. So helium has 2 valence electrons. For neon, the outermost level is 2, and there are 2 electrons in the 2s, 6 electrons in the 2p, for a total of 8 electrons in level 2 altogether. So neon has 8 valence electrons. For argon, the outermost level is level 3, and the total number of electrons in level 3 is 8. So we have 8 for argon. For krypton, the outermost level is 4. There are 2 electrons in the 4s, 6 electrons in the 4p, and so there are 8 outermost electrons here as well. And then for xenon, the outermost level is 5, and there are a total of 8 electrons in shell 5. So helium is kind of an exception. It's a small element. It cannot really fit 8 electrons in the outermost shell, but the rest of these noble gases are following the pattern that they have 8 valence electrons. They have a full outer shell. So having 8 electrons is extra stable. These shells are completely full, and so a lot of other elements are trying to get to have 8 electrons in their outermost shell as well. Some of them form ions to do that, some of them form bonds to do that. A lot of the chemistry we see are things that elements do to try to get 8 electrons in their outermost shell. And this is called the octet rule. So a lot of elements are trying to get 8 electrons in their outermost shell, and their chemistry, the chemistry that they do is them trying to get that. Since these noble gases already have 8 electrons in their outermost shell, they do not react very much with other elements. They're pretty unreactive because they're happy just the way they are. They're kind of lazy. They don't like to associate with other elements. That's why they're called the noble gases. They're too good for all the other elements here. Let's do some more electron configuration for some of these elements and ions. These are all alkali earth metals, so when we do the electron configuration, we can tell how they are similar. We're also going to take a look at abbreviated electron configurations. To abbreviate the electron configuration, it uses the noble gas from the previous period. So if you are trying to do an abbreviated electron configuration for an element that's in the 4th period, you would go up to the 3rd period, so you would go up 1 square and then go all the way to the right to find the noble gas in that 3rd period. So lithium has 3 electrons. The first 2 are going to go in the 1s orbital, and the next one is going to go in the 2s orbital. The 2s orbital can fit 2 electrons, but lithium only has 3, so we don't want to put 2 in there because that would be 4 electrons. We want this to add up to 3. If we go up to the 1st period, because lithium's in the 2nd period, if we go up 1 square and all the way to the right, we find helium. So the abbreviated electron configuration uses helium. Helium's electron configuration is just the 1s2. That's what helium is. That's the electron configuration of helium anyway. So besides the electron configuration of helium, lithium also has 1 additional electron in the 2s orbital. So we can write lithium's electron configuration as the electron configuration of helium plus 1 more electron in the 2s orbital. For this particular element, it doesn't make sense to abbreviate it because it probably took more writing to do helium in brackets than it did to do 1s2, but it makes more sense as you go along. For example, sodium with 11 electrons, the first 2 going to the 1s orbital, then 2 into the 2s orbital, then 6 into the 2p orbital, and then 1 into the 3s orbital. When you go 1 square up and all the way to the right, you find neon, the noble gas there. Neon has the electron configuration 1s2, 2s2, and 2p6. So all of this is the same as neon. In addition to neon, there is this 3s1. So we can say that sodium is like neon with a 3s1 added onto the end. Let's skip the ion for now and go ahead and do the other alkali metals that we have here. We have potassium with 19 electrons and rubidium with 37 electrons. The 19 electrons of potassium go into the 1s orbital, the 2s orbital, the 2p orbital, the 3s, the 3p, and then start on the 4s to add up to 19 electrons. And then for 37 electrons, the first 2 go into the 1s orbital, then 2 in the 2s orbital, 6 in the 2p orbital, 2 in the 3s orbital, 6 in the 3p orbital, 2 in the 4s orbital, 10 in the 3d orbital, 6 in the 4p orbital, and 1 in the 5s orbital. So all these superscripts add up to 37. 2, 4, plus 6 is 10, 12, 18, 20, 30, 36, 37. Potassium is in the 4th period. If we go up to the 3rd period and all the way to the right, we find argon. The electron configuration of argon is all of this stuff over here. So we can replace this with argon in brackets because the argon electron configuration is equal to this. In addition to the argon electron configuration, there is one more electron that goes into the 4s orbital. The noble gas in the previous period for rubidium is krypton. Krypton has 36 electrons. So these first 36 of the 37 electrons of rubidium are the same as the krypton electron configuration. And then there is one more electron that goes into the 5s orbital. One advantage of these abbreviated electron configurations is that it makes it more obvious how these elements are related to each other. You can see the family resemblance in this family of alkali metal elements. They are all exactly like a noble gas, which is a nice complete electron configuration, plus one extra or one additional electron beyond what the noble gas would have. So that's what makes these very reactive. It's like these elements are almost exactly like the cool kids of the periodic table, the perfect electron configurations of the periodic table. So it's almost like a kid going to school and they have the perfect outfit, but then it's cold, so their mom makes them wear a dorky hat. When they get to school, the first thing that's going to happen is that these kids are going to lose the dorky hat. And that is what's happening in those alkali metal videos where you see different metals being thrown into water. They hit the water and they react explosively, trying to get rid of this one extra electron and become an ion with a +1 charge. I should have written a 1 here. This is the old way I used to write +1 charge with just a plus, but we're supposed to be writing it 1+. So sodium with 1+ now has 10 electrons. It has lost one of the electrons, and so now it has the exact same electron configuration as neon, the cool kid in the 2nd period of the periodic table. So that makes sodium much more stable. When it's a +1 charged ion, it has a much more stable electron configuration than when it has this additional 11th electron. So that's part of what's making sodium very reactive. And it also makes potassium very reactive. Potassium would much rather have only 18 electrons and be a potassium ion with a +1 charge. That would give it the same electron configuration as argon. So this is how these alkali metals try to get a perfectly filled outer shell with 8 valence electrons. If you'll notice, right now, sodium has 1 valence electron, but it really wants 8. When sodium is the ion, it no longer has any electrons in the 3rd shell. All the outermost electrons are in the 2nd shell. So sodium ion actually has 8 valence electrons, making it like a noble gas. And that is how sodium likes to be able to follow the octet rule by losing that 1 electron, so that now it has 8 electrons in its outermost shell. So when these alkali metals are not charged, when they're neutral, they have 1 valence electron. So uncharged, these elements have 1 valence electron. When they form an ion with a +1 charge, these two cases over here, then they have 8 valence electrons. So the chemistry that these elements do is based on their electron configurations. These electron configurations are for the alkaline earth metals. Magnesium has 12 electrons when it is neutrally charged, or when it's neutral, uncharged. So 2, 4, plus 6 is 10, plus 2 is 12. These first 10 are the same as neon. So we can abbreviate this as neon with 2 more electrons in the 3s orbital. Again, let's skip these ions for now and take a look at just the neutral elements. Calcium has 20 electrons, strontium has 38 electrons, and barium has 56 electrons. I'm going to keep going until my superscripts add up to the number of electrons that I have to find spots for. And I'm using the order that we talked about for the order that the orbitals fill in. So calcium with 20 electrons is very similar to argon with the 18 electrons, with 2 more in the 4s orbital. Okay, so here I have found spots for the 38 electrons of strontium, which is very similar to the 36 that are in krypton, plus another 2 added onto that afterwards. Okay, I had a little bit of trouble squeezing all 56 electrons in here, but the first 54 are just like the electron configuration of xenon, and then afterwards there are 2 more electrons that need to be added in the 6s orbital. Again, the abbreviated I think makes it a little bit easier to see than all this stuff over here, that these all have 2 valence electrons. So the outermost level here is the 3 for magnesium, the 4 for calcium, the 5 for strontium, and the 6 for barium. And these outermost levels have 2 valence electrons in them. So all of these have 2 valence electrons, but they really want to have 8. They want to be just like these noble gas configurations that have 8 valence electrons. And so the way that these elements do that is to lose 2 electrons. So if you have an outfit that's just like the cool kid outfit, but then you have a dorky hat and also a dorky scarf that your mom made you wear, then when you get to school, you're going to take your backpack and shove your hat and scarf in there so that those will be gone and you'll have your perfect outfit again. So that's what these guys do. They lose 2 electrons so they can get their perfect electron configurations back. Magnesium with a +2 charge has 10 electrons, and so it has the same electron configuration as neon with 8 valence electrons. Calcium with a +2 charge has 18 electrons, which is exactly the same as argon. So now its outermost electrons are in the 3 shell, and it has 8 valence electrons. So when the alkaline earth metals react, they like to lose 2 electrons and become +2 ions. This chart has electron configurations for the halogens. So fluorine has 9 electrons. The first 2 go into the 1s orbital, then the 2s, then the 2p orbital is not quite full. So this is 1 electron short of being like neon with the 10 electrons. So if we want to write the abbreviated electron configuration, we can't write neon because there's not a full neon configuration here. There's a full helium electron configuration, and then 2s2, 2p5 after that. So chlorine has 17 electrons, the 1s2, 2s2, 2p6, 3s2, and then there's only 5 electrons left to go into the 3p orbital. So it's 1 fewer than what argon would have. So instead we'll have to abbreviate this as neon. This part is like neon, these first 10, and then we have 3s2, 3p5. Then we have bromine with 35 electrons. It's 1 electron short of being like krypton. So instead we'll have to abbreviate this part. This first 18 electrons are like argon, and then we have another 17 electrons after that, 4s2, 3d10, 4p5. Iodine with 53 electrons is 1 short of being like xenon. So instead we're going to have to abbreviate it like krypton. So these first 36 electrons are just like krypton, and then we have another 17 electrons after that. So again, we can see in these abbreviated electron configurations the family resemblance in this halogen family of elements. All of these have 7 valence electrons. The outermost electrons are in the 4th level. These ones are only in the 3rd, so we have 7 that are in the outermost. Since all of these have 7 valence electrons and want 8 valence, all the elements want 8 valence, then the most obvious thing for these elements to do is to gain 1 electron and become a -1 ion. Then they would have 8 valence electrons. So fluorine with a -1 charge would have 10 electrons, making it just like neon at this point, now with 8 valence electrons. The same thing with chlorine. When it forms a chloride ion with a -1 charge, it has 18 electrons, and that makes it just like argon with 8 valence. So these elements get their 8 valence electrons by forming anions with -1 charge. Let's do a few more elements from the P area of the periodic table. If you find these on the periodic table, you'll see they're in that main group elements on the right hand side where those 6 columns are. And like the halogens that we just did, they are filling up their p orbitals. So when we finish these electron configurations, we'll see that they are in the process of filling up a p orbital. So carbon with 6 electrons is filling up a p orbital. It does not have enough to completely fill the p orbital. Then it would be like neon. It doesn't quite have that. It has a similar electron configuration to helium with some more added on after that. Silicon with 14 electrons is in the same group, the same family of the periodic table as carbon. And so we can see the resemblance. We are also putting 2 electrons into a p orbital when we end our electron configuration. So silicon is like neon with 4 additional electrons. Both of these elements have 4 valence electrons. So you can see a family resemblance there. Sulfur and oxygen are also part of the same family as each other. They're a different family from carbon and silicon. So we have 16 electrons for sulfur, 8 electrons for oxygen. So sulfur is ending its p orbital with 4 electrons in it. And oxygen is also ending its electron configuration with 4 electrons in a p orbital, the 2p instead of the 3p this time. And so both of these elements have 6 valence electrons. Oxygen and sulfur with their 6 valence electrons want to have 8 electrons, 8 valence electrons, and so they tend to form ions with a -2 charge. Gaining 2 more electrons brings them up to 8 valence electrons. So oxygen with a -2 charge, called the oxide ion, has 10 electrons, which has the same electron configuration as neon, with 8 valence electrons. This table has a few elements that are transition metal elements and some lanthanide elements. And so the transition metal elements are going to be ending their electron configuration while they're in the process of filling a d orbital. And then lanthanides are going to be filling an f orbital. The problem is that some of the heavier transition metals and the actinides, for sure, a lot of actinides and some of the lanthanides have exceptions, meaning that they don't fill their orbitals in quite the way that you would expect. And so I don't want to do too many of those. I think I'll show you this one because this is the most common one that textbooks address. But I'm not going to do palladium. I think instead of palladium, I'll do cadmium instead because that one's not an exception. These 3 are not exceptions. These 2 are not exceptions, so we'll be able to fill those in the regular way. So titanium has 22 electrons. So we fill the 1s orbital, the 2s and the 2p orbital, the 3s and the 3p orbital, the 4s orbital. That brings us up to 20, and there are 2 more that are going into the 3d orbital, because the 3d is the one that comes after the 4s. And this is just like the electron configuration of argon with 4 additional electrons. So cadmium has 48 electrons. So these 48 electrons fill up the first 36 the same way that krypton would, so filling up to the 4p, and then there are 12 more electrons to put in after that. The 2 go into the 5s, and then 10 going into the 4d. So manganese with 25 electrons puts the first 18 into the same orbitals that argon would use, and then 2 more to make it to 20, and 5 more going into the 3d orbital to get 25. So the reason why some of these exceptions occur is that a completely full orbital or a half full orbital are more stable. So it's just helpful to have a half full orbital or a completely full orbital. And since D can fit 10 electrons, having 5 electrons in the 3D adds a little bit of extra stability. It lowers the energy. So if we go back to our theater analogy, it's kind of like if you buy the D section tickets in sets of 5, you get a little bit of a discount. And so there's an incentive to have the D with 5 or 10 electrons in it. So let's put what we expect here for chromium with 24 electrons. So we would expect chromium to have 4 electrons left to go into that 3d orbital. But like I said, the 3d orbital prefers to either be half full with 5 or completely full with 10. And since it's so close to being half full, what happens is that one of these electrons can be borrowed. It can borrow one from the 4s. So instead of having 2 in the 4s, we have 1 in the 4s. And that 1 can add to the D, bringing it up to 5. So this makes chromium an exception. It's a little bit unusual. You would expect to put 2 electrons in the 4s and 4 in the 3d, but instead there's only 1 in the 4s and there's 5 in the 3d. So this is what makes it an exception. This part over here is kind of unusual. This is the exception part. Okay, so now we have some lanthanides that we can do. One of them with 68 electrons and another with 60 electrons. So I've picked these because they don't have these exceptions in them. They fill up in the order that we would expect, and we do expect them to be finishing their electron configurations by partially filling the f orbital. That's what the lanthanides and the actinides are doing. That's the F section of the periodic table. All right, so here are 68 electrons here. We have 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 54. These first 54 are the same as xenon. And then we have 14 more to bring us up to 68. So it's xenon with 14 more. After the 6s comes the 4f. So the last orbital that is being worked on is the 4f, and it's not quite full yet. It has 12 out of the 14 spots filled up for this element. And then for this one, it's similar. So for this element, we have the 54 of xenon plus 6 more, 2 going into the 6s and 4 going into the 4f orbital. So these lanthanide elements are filling up the 4f orbital. That's the section of the periodic table where they are located.